Section 1.7 is combinations of functions, and part of that is dealing with composite functions. So before we get started on the composites, let's talk about domain. Domain is the set of numbers that of all possible x values. In other words, your input values, which can also be called our independent variables. What are the things that are put in place for x that we can use in a function? So for example, if you have the function f of x equals 3x plus 1, the domain here is all real numbers. In other words, any x value can be put into this function and we will get a valid result. Remember, we talked about another way to write all real numbers is this symbol with the double bar. If we use our set notation, or our interval notation, will be negative infinity to infinity. So let's look at one where there is a restriction on the domain, where the domain has to be defined. For example, f of x equals 1 over x minus 4. In this case, x cannot equal positive 4 because that would give us an undefined value. When we plug it in, we would get 1 over 4 minus 4, which is 1 over 0. So we can write this a couple of different ways using our set notation. It is the set of all x values such that x is a real number and x is not equal to 4. We can also use our interval notation. So we can go from negative infinity all the way up to 4, but not inclusive, and then we can combine that or do the union and use the set from 4 to positive infinity. You can see that the value of 4 is not included in either of these intervals because this is an open parentheses, and so therefore we're really saying from negative infinity to infinity and exclude 4. So when we have a denominator, we need to be very careful of our domain and make sure that we don't choose x values that would make the domain 0, make the denominator 0. Another time we have to watch out for domain is under a square root or any even root. So for example, the square root of x plus 2. We know that we cannot take the square root of a negative number, so the value under the square root cannot be negative. Therefore, for this function, my x values have to be greater than or equal to negative 2. Take a look here. This is one of our transformations. This is a shift to the left 2 units. Our parent function would have looked like this. Our shift to the left 2 units would look like this. And you can see why our domain has to be greater than or equal to negative 2. Let's write this domain in our set notation. So in set notation, it would be the set for all x such that x is greater than or equal to negative 2. For our interval notation, we would say from negative 2, and we're going to include it this time, so we use the closed bracket, up to infinity. Okay, take a moment and see if you can do domains for these two functions. F of x equals x squared minus, let's use plus 3x minus 17. And f of x equals 5x over x squared minus 49. See if you can find domains for those using either your set notation or interval notation. Pause the video. Okay, the solution to this one, this is a polynomial. It is a parabola that opens up, and the domain here is all real numbers. There is no restriction on x values. They can go on and on forever, right and left. And although this isn't really going through 0, 0, it's down here at negative 17. But nonetheless, you can see that this function can go to the right and left as far as we want. So it's all real numbers. For this one, we have to worry about our denominator, and we have to see make sure that this binomial does not equal 0. I used factoring to solve. Therefore, x cannot equal 7, and x cannot equal negative 7. So using our interval notation, we would say negative infinity to negative 7, negative 7 to 7, and then 7 to infinity. Okay, so there's a couple examples of domains. Now we can do certain operations on functions. Go ahead and take a minute and write this down, then I'll come back and talk about it. Okay, so all this is saying is that if I have two separate functions and I want the composite of those two, all I have to do is add the functions individually. This is very, very simple. Don't make it harder than it is. So for example, we have the function f of x equals 2x and g of x equals x minus 1. Then f plus g of x would be 2x plus x minus 1, or 3x minus 1. F minus g of x would be 2x minus x minus 1. Watch the parentheses there. 2x minus x plus 1, or x plus 1. Multiplication and division work exactly the same. Again, using these two functions one more time. F times g of x would be f of x times g of x, multiplied to get 2x squared minus 2x. And the final, which would be f divided by g of x, would give me 2x divided by x minus 1. So very, very simple operations. The only thing that we need to look at here, in addition to the fact that we can very simply combine two different functions together, is what happens to the domains in this case. Well, when we're adding two functions together, the domain of the combined function is simply the union of the domains of the original functions. So in this case, for our first one, the domain of f plus g of x is simply the domain of f of x plus the domain of g of x. Okay, so all you have to do is find the domain of the individual functions and combine them. The one we have to watch out for here is division, because when we divide, the domain of f divided by g of x is the domain of f of x and g of x, but we have to make sure, sorry about that, we have to make sure that the domain of g of x does not cause the function to equal 0. So we just have to watch that denominator as we did before. We've done these before again, and now we're going to move on to our composite functions. We've done this as well. They, again, use a little different notation. This little o, that's just a little tiny letter O. F of g of x can also be written this way, and that's what we've done before. Take a moment and write down this domain information. Okay, so the domain of f of g of x composite, and I'll do an example for you in a moment, has to make sure that that x is in the domain of g and that the result is in the domain of f. And I'll explain that in just a moment. But let's do one first. So, for example, if f of x equals 3x and g of x equals x minus 2, and I'm trying to find f of g of x, or f of g of x, same exact question, different notation. What this is asking me to do is to take the function f and evaluate it at g of x. So that's going to be 3 times our x minus 2, which is 3x minus 6. Since the domain for both of these functions is all real numbers, the domain of the resulting function is all real numbers as well. Now, if I want to do g of f of x, that says I'm going to evaluate my g function for 3x, which means I'm plugging 3x in place of x here, and that gives me 3x minus 2. So composites you have done before, and we just need to be careful of our domains. Again, since all of these are all real numbers, we don't have any question about domain. But let's take a look at another example. So let's say f of x is 2 over x minus 1, and g of x is 3 over x. First, let's look at the composites. F of g of x, well, that's f of 3 over x, which means that this is taking the place of x. So 2 over 3 over x minus 1. Now, I need to clean this up a little bit. Common denominator in the base, bringing these two fractions together, and then multiplying by the reciprocal. So my final result is 2x over 3 minus x. Now let's go back and look at domains. The domain of this original function is all x values such that x does not equal 1. The domain of this function was x could not equal 0. Now, we have to make sure that this function also meets our restrictions. So, looking back, we want to make sure that in addition to being able to use our original function g of x, where x could not be 0, we also have to make sure that when we plug into our f of x that we do not create a new problem. So our domain here will be negative infinity to 0, and then 0 to 3, watching out for this denominator, and then 3 to infinity. You can see that since we've replaced the f of x denominator with this, we no longer have to worry about our function for x not equal to 1. We do have to watch out for 0 here, but we no longer have to worry about our 1, and we have to worry about our result. So we look at the inside function and the resulting function. Let's try one more of these. I'm going to erase, but I'm still going to use these two functions. And we're going to do our g of f of x, which means that into the g function, I'm going to put this equation. So now I've got 3 over 2 over x minus 1, which is 3 times x minus 1 over 2, or 3 times x minus 1 over 2. And you can see that although in the result of the function there is no restriction, I still have to be mindful of the original denominator that went into this domain. So our domain here is negative infinity to 1, and then 1 to infinity. We'll be spending quite a bit of time on this in class, so we'll make sure everybody gets the hang of it. The last thing we'll look at is decomposing functions. Now all this means is that when two functions have been combined together, we can do the same thing in reverse and undo the composition. Let me give you an example. If h of x equals the cube root of x squared plus 1, I could say that this came from two separate functions, one being an inside function of x squared plus 1, and one being an outside function of the cube root of x. And hopefully you can see now that if I did the composite, f of g of x, that would be f of x squared plus 1, or the cube root of x squared plus 1. So if we're given a composite and we define two other functions, we can now say that h of x is a composite of f of g of x. And you can really pick any two functions you want, whatever splits it apart the easiest. Let me give you another example to try. If I tell you that h of x is 7 over x minus 3, can you think of two functions that might have been combined to create that? I'll give you a minute. Okay, what I did was I said that if g of x is x minus 3, and if f of x was just simply 7 over x, then when I do the composite, I am putting 7 over x minus 3. Again, take a look at a couple of the examples in the text. There's more than one way to do the decomposition here, so please feel free to play around with it and see what you can do, and we will talk about this in class time. All right, we'll see you in class.